Good afternoon. Thank you for coming. You just all had lunch, right? And you've scooted all the way over here to see me, and I've got a song and dance for you I hope that you'll like. How many of you are actually awake after this morning's festivities? It's been a long day already, I bet. Raise your hand if you're with me. Are you with me? Okay, there's some activity in the front. That's good. In the back, are you playing games on that laptop, or did you? No? Okay. Really? Because I want you to listen? Okay. So I hope you're all going to listen. I have just a few things to say, and I'm going to try to make it a little bit light and fun. It's a lunch session, and I kind of want you to have a good time. I'm Rico Mariani. I'm on the CLR team. I'm a performance architect. And they asked me to come out here and tell people the top 10 things I would tell them to write better performing managed code. And I thought, okay, I got a room full of people. They're going to be writing all different kind of applications. What 10 things could I possibly pick? And then I remembered my top 10 advice is the same for everyone. And it goes something like this. To have great performance, I want you to measure, 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 measure. What, was that 10 or was it? Measure some more. Anyway, measure. So the trouble with that advice, though, is that it doesn't really make for a good 45-minute talk. And there's lots more, things that I'd like to tell you about the CLR that maybe is kind of useful to you. So putting aside the fact that I think that measuring is the most important thing any of you could do to get good performance out of the managed platform, I still think there's some things I want you to know. So I decided to kind of stand the topic a little bit on its head, and there's some things that we did in the CLR that I'm really excited about, things we worked really hard on and that I think will make a difference to you and to your customers. So I want to share those with you, and I want to kind of put them in context in terms of sort of what they mean to you and what you might do to take advantage of them, and how maybe that's a little different than Everett. So that brings us to what's new in the would-be CLR and why you should be pleased. Now, I guess on this point, I want to just mention that I'm a CLR guy, and so today I'm going to be talking about features in the CLR, okay? And that's way down here low in the stack, okay? So we deal with things like strings and garbage collecting and assembly loading and primitive kinds of operations. So I'm not going to be talking to you about what's new in ASP.NET. That's cool for perf, because I'm really not the right guy to talk about that stuff, and I'm not going to be talking about what's new in WinForms. That's good for perf. I'm kind of stay low to the metal, okay? So, which isn't to say that there aren't new and cool things in those areas, because there are, but I'm not going to be talking about those today, okay? So with that, I'm going to start with what I think is the most important thing that we did in the CLR for you guys and for your customers. We made significant improvements in our engine technology. Raise your hand if you know what engine is. I know what engine is. Some people know what it is. Half of you know what engine is. Engine stands for native image generation. Some people call it the pre-jitter. Okay, and that's where we can take your IL assemblies and compile them before they're used into native code so that they look a lot more like conventional DLLs. Now, why is that important? Well, it's important because when you JIT code into your process, you can't share that code with other processes. Right? It's dynamically allocated. It looks just like data to the system. It goes into the swap file. You get private pages as far as the system's concerned. Well, private pages are fine, and JITting is fine, and it works great for a large class of applications. But if you have large libraries, you want those libraries to be shared across all the managed code that's running throughout the system. And you want the system to be able to cache those pages, reload them, remember them. So if you run the same application twice, it comes up more quickly. And all those other good benefits that you get out of native code for traditional unmanaged applications. Before would-be, it was the case that even if you engine the application, a good chunk of the data wasn't shareable because we were doing things to that image to mutate them. We used to modify upwards of half of that image. And so that means half of the possible benefits are down the drain, right? So in would-be, we really went to task on this, and we dropped to more like 10% of the pages. And we want to go even lower. In some cases, we are lower. More like 10% of the pages are dirty. So that means 90% of the image is shareable. That's great news if you're running more than one application, right? Because things like MS Core Lib, our main BCL library, system.xml, system.dll, those assemblies, they're going to be loaded at a much reduced cost for you. So what does that mean for you? It means if you're shipping libraries think again about whether NGen is a success for you. Lots of people were walking away from it because it wasn't worth the hassle in Everett. We think you should look again. We think you'll be pleased. So a lot of assemblies, especially on client-side applications. Many people writing client-side applications, they find themselves a little bit tight on memory. You know, they want to run on that small machine. They want to run on mom's computer. And they want to deliver a managed application. If you NGen, you'll find that things are a little bit more frugal. Okay? And that means you can get more managed code in that same box, and you'll be able to target mom's machine. So have a look at that. All right? These savings in private pages translate directly into startup time savings in most cases, because startup time is gated by I/O. So whether you're starting cold, first run, less I/O means less disk hits. Less disk hits, it comes up faster. We like coming up faster. Or starting warm, that means we've seen those pages before. They're going to come clean off the disk. They're going to be right at the disk cache. They can be mapped directly into memory without change. More pages, more directly mapped, faster startup. Okay, so this right here, more sharing, is probably the most significant thing we did, and certainly it was the bulk of our effort in this release. All right, there are some funky features to help this work better, so I want to tell you a little bit about some of the things we did. The first one is, well, we call it hard binding, and I'm actually going to kind of give the trailer version of this. Imagine this is a movie. You're only seeing the trailer today. In 45 minutes, I can't really show you the whole movie, and I don't even really want to get into the details of what are all the funky names and what are all the funky attributes. Later on, there's a link to my blog, and I've written about a lot of these things and some other topics over the last couple of months, and there'll be more articles coming forth. And in fact, I encourage you, if you have more detailed questions after this session, go ahead and visit that blog. I'll make a posting, and you can go and ask me directly, and I'll try to get right to it, and I can give you the nitty-gritty as to what attributes are the most interesting ones. So, but let me go through these three technologies. Hard binding is about telling the CLR that certain dependencies strongly depend on one another, and that it should assume that the one is going to be loaded before the other and at its preferred load address. Okay? Who knows what a preferred load address is? Raise your hand if you know what a preferred load address is. Okay, even less people know what a preferred load address is. Preferred load address is the standard place at which a DLL or an executable is to be loaded. Okay? If it gets its preferred load address, meaning if that memory is available for use and the Windows operating system can put it at its preferred load address, there are no relocations need to be applied. It doesn't need to be adjusted. You can just plunk that memory right there. If we don't get the preferred load address, adjustments have to be made, and that translates to more private pages and more work at load time. So if we make assumptions about which DLLs are being loaded and where they're going to be loaded, we can generate tighter code in the native assemblies to make direct calls to some of those things. Less indirections, that means less space, it means less private pages, it means better performance for you. Okay, so in some cases, it's useful to use hard binding to strongly link assemblies together so as to eliminate some of those private pages. This is going to be important to you if you have large libraries, right? Okay? So if you're shipping 5, 6, 10, 20, 50, 100 assemblies, you want to think about minimizing the private pages that you have associated with those assemblies so that you minimize the need for memory on the client boxes you're going to hit. String freezing is another one that is on the same path of trying to minimize the amount of touching that we have to do on the heap, and you're just using the standard load mechanism to get the system up and running with minimal cost. String freezing is where we take string literals that occur in your executable, and rather than put them on the GC heap like we used to, we actually burn a copy. I say burn, but you know, what's the right verb? A copy of that string literal in its native CLR object format is present directly in the native image. So at startup time, rather than having to intern the string or make a copy of the string or load it from the user resources like we usually do and then make a copy on the heap and then compute what the pointer is, we can use that address directly in the image. That's usable in assorted images that are going to be highly shared. We turn on string freezing for images like MS Core Lib, for WinForms, okay, for system.dll. Those images tend to be loaded and they tend to stay, and they tend to be used by a lot of different people. So having the string literals already burned into them is a good savings in terms of space. And it basically converts those private pages that would have been on the GC heap into shared pages that are in the executable, like the others. Okay, I already mentioned setting the base addresses. There's opportunities to set the base address in the engine command line parameters and via attributes. I'm not going to go into those now, but you definitely want to think about how you're going to stripe the memory if you have, say, 50, 60 DLLs. Some people have a lot of assemblies, and that's an important part of how they deliver because it gives them good servicing or other important attributes that they want in terms of pluggability or whatever else. Those DLLs need to get a good base address because if they don't get a good base address, the default will be the same for them all, and only one can possibly be loaded at the preferred load address. We've had customers realize significant savings by just thinking about striping those DLLs the same as they would with unmanaged DLLs. Okay? And we now give you the opportunity to do that. Now, I'd like to be standing here telling you, you know what? We do this all automatically. We figure out what strongly depends on what. We figure out what are good base addresses for various different cases based on some very cool heuristics, but we're not there yet. In this release, we've gone a long way down the path of eliminating private pages and improving the load time and reducing the cost that is associated with just having these assemblies in memory. But we are not all the way down the path of having an automatic system that knows what should be engined and what shouldn't be engined and how to choose base addresses for all of them. So there still remains some work for you if you're building sophisticated client-side applications especially. On the server side, people have had more positive experience just using the JIT because they're much less sensitive to startup issues and often less sensitive to working set issues as well. Servers tend to have big, burly, amounts of memory, and the code size is often not a dominant factor in the total memory requirements for the system. However, contrary-wise, where people are running on things like Windows Terminal Server, where there could be 500, 1,000 different sessions, okay, with client-side apps effectively being present on the server, these issues are magnified tremendously, right? Because there's not one copy of the application running. There could be 500 copies of an application running for independent users. So those shared pages make the difference between having a nice, crisp system that's able to support 500 users or having a system that's paging to death, right? Okay, so shared pages and engine improvements. Big on my list, and it's my top 2. All right, generics. Some great things you can do with generics in this release. I don't know how many of you had a chance. Well, okay, raise your hand if you had a chance to play with generics at all during the beta. Do you know? And now raise your hand if you even know what I'm talking about when I say generics. Okay, so almost everyone knows what a generic is, and some of you had a chance to play with them. That's great. So one of the reasons people talk about adopting generics, and one of the benefits you get because of generics are present in this version of the CLR, is that they give you a way to eliminate boxing, right? And people kind of worry about boxing a lot. They have collections and they're holding, comparatively small objects, maybe lots of those objects, okay? And they don't want to have 5,000, 10,000 boxed integers coming in and out, or boxed value types. Using generics, you can eliminate those boxing costs and effectively create types like list of your value type, where there's no overhead associated with each entity in the collection. That's good news for you. And iterating over those collections gives you some significant benefits as well, because you have superior locality. If they're all in a nice array, you're going to get nice contiguous behavior, and so memory utilization is going to be better. All of that's good news. Secondly, you get the strong typing benefits, right? So much easier to write correct code and make sure you're picking up the right collection in the right place. No casting or unboxing costs when accessing elements. So even if space isn't an issue because the collections are small, overheads for unboxing can be good. But there's a caution here. Each instance of a generic type that you create, and I've written about this, has a small cost associated with it in terms of the code and method table overheads. Code for generics can be shared for all reference types. So once you've created, say, list of object, that's usable for list of any reference type. But for value types, that's not the case. So if you make list of your object and list of my object and list of his object, there'll be 3 separate copies of the code. For lists, the cost of creating a new list class like that is about 8K, most of which is shared in the engine case, which is really good news. It actually ends up being only something like 50, 60 odd bytes of private bytes for each list item. So translating that into boxing savings, it basically says if you're going to store about 500 objects in your collections simultaneously, then you're going to come out ahead by using generics on space because you'll save the cost of boxing and you'll instead be paying the cost of the generic implementation. you'll come out ahead at about 500 items, and you'll be cashing in on the generic savings and eliminating the boxing. So on the other hand, if you have lots of different kinds of collections that have comparatively few items in them, you could easily create a disaster, right, by making, list of this, list of that, list of the other. It's never been easier to burn 8K, with just 4 or 5 characters, list of, X, right? And what is that? 7 characters? 7 characters, I've blown 8K. So that's like 1K, over 1K per character. So I have to be careful, right? I have to be very careful that I don't go crazy generating generic types all over the place. But on the other hand, it doesn't take much for the generic to pay for itself. Now, other classes like dictionaries or your own generic classes could have additional complexity and additional cost associated with them because, well, for instance, dictionaries are more complicated than list, right? So you can expect that the marginal cost for a dictionary is going to be more like 12K rather than 4. It's about half again as complicated. And your own generic types could have additional collateral costs associated with their complexity. But ultimately, we find that generics is a net saver of memory, especially because those generic costs that I told you about, remember, they're shared costs, right? Not private costs. And we like shared pages, right? Shared pages can be preloaded, they can be shared across processes and so forth. Boxing costs cannot be. All right? So don't go crazy, but do go ahead and use generics for your needs where you have significant data storage. All right. A common rumor is that ForEach is bad. Maybe I contributed to the start of this rumor. Generally, people think, oh, well, I should use, for the best speed, I should use 4 instead of ForEach. Definitely 4 instead of ForEach. ForEach is bad. 4 is good. And I've actually written several articles kind of in this space. And so I think this is as good a time as any to kind of clear the air a little bit on this. The biggest problem I ever had with ForEach is that it just so happens that the way that ArrayList, our v10 implementation of ArrayList, the way that ArrayList implements IEnumerable, okay, causes the standard ForEach behavior to be more expensive than I would like it to be, a good bit more expensive than I would like it to be. Now, even that is not a total disaster. And in fact, most people use ArrayList and ForEach over ArrayList and never have a performance problem, and they could just ForEach with impunity. Because for the most part, there's just not enough ForEaching over enough ArrayList for that to be even remotely near what your top problem is. I guess secondarily, a lot of times when people even measure this cost, they do it in the context of a very small benchmark that's doing nothing but ForEach over an ArrayList. And in real code, you don't just ForEach over an ArrayList and then throw the results away, right? You do like actual work on each item, and the actual work ends up being where the cost is and not these, virtual call overheads. But be that as it may, the problems that were in ArrayList that caused the implementation of IEnumerable to be less than it should have been, which we're stuck with, were fixed in the generic implementation. So if you use list of object, for instance, which is functionally equivalent to ArrayList, you'll find you have none of those issues. And you'll find you get a good factor of 2.5 speed improvement just using ForEach in the same kind of way. And you'll also find that there's no memory allocation overhead. All right? So in terms of eliminating the extra cost of memory allocation and reducing the cost of virtual calls, we are already there with generics. Now, I think there's still cases where if you go right to the metal and you really need to eliminate the bounds checks and you really need to, iterate over, potentially a very large array list and many, many times, you might find that you want to use some of the more extraordinary features of the .NET system to go ahead and improve that performance. But that's the rare bird, okay? For most people, most of the time, you're not going to have performance issues if you're just doing plain ForEaches over lists, especially list of object, and you're not going to have any of the allocation overheads that were present before. I tend to encourage people, I tell people that one of the strengths of the .NET system, and this strength is present in many places, is that it does not box you in to one choice. You do not have to ForEach over every array. You could choose something lower. You do not have to use safe access to every array. You could use unsafe pointers. Now, we don't want you to go and reach for those tools in every little situation that comes along, but we like that those things are available to you when you need them. So if 99% of your program is just fine with ForEach and doesn't have any problems, and maybe all of your program for most of the time, right? In the one place where you really need it and you profiled it and measured, remember I said measure at the beginning? You measured that that's a hot spot and you need the extra performance there, you've got that tool in your arsenal. But please don't turn that into general advice that, where, oh, Rico said don't use ForEach because it's too slow, because that's not the case at all, right? Generally speaking, our guidance is to go ahead and use the primitives. And as you've seen today, and over the last couple of days, we have new and exciting features built around using ForEach, and we're spending a lot of time thinking about the performance of those various different things, right? The link features are all about doing enumeration. We're big believers in enumeration, so I don't want you to leave here thinking, hey, Rico's advice is don't use these complex enumeration features, because that's certainly not the case. Most applications won't be affected by use of ForEach. Significantly improved and reduced overhead in Whitby, and so pretty much you can ForEach over your collections, guilt-free, right? All right. Some more low-level changes in the garbage collector. My favorite thing about this advice is you almost have to do nothing to get these benefits. There's assorted changes were made. One of my favorites is that there's now some time-based criteria associated with the garbage collector. So even if your memory usage starts to diminish and you don't reach the point where we normally would have scheduled a garbage collect for you because you had demanded enough memory, we might go ahead and schedule that garbage collect a little bit early, right? Because we're saying, hey, you know what? It's been a long time since that last collect. There should have been one by now. And maybe we need to reevaluate our trend here because the statistics sometimes change. Really, one of the things that people have had problems with in terms of getting the best mileage out of the collector is that the garbage collector is very good at the steady state kind of case where its projections as to how you're using memory tend to stay valid, or for fairly smooth transitions. Where you have sharp transitions, right? Like for instance, a giant dialog is just closed and a bunch of objects that weren't slated to die or had been living for a very long time suddenly die. Okay? Those sharp transitions are astonishingly difficult to predict with any kind of statistical analysis. However, some of the time-based features we have will help you out because we'll notice in a passing of a small number of seconds that, hey, we should do a collect and reevaluate and see, what our new current allocation rate is, and that will tend to reduce your overall memory demand and just make the garbage collector that much more effective for you. Now, I continue to give people advice that they should call gc.collect after big episodic events like a big dialog shutting down, a large document being closed, simple one-time events that are easy to detect in your application that sort of have caused mass extinction of objects. Those things are very difficult for the GC to catch and very easy for you to catch. And you can instrument your code with, well, not instrument, but rather inject garbage collections in appropriate places in your code in a small number of places and find that the garbage collector is more responsive for you. Another thing that we did in this release is the two flavors of garbage collector were merged into one version of our executable. Now what's good about that is that it means that you now can easily configure which flavor of garbage collector you get. You can choose the server garbage collector even if you're on workstation. You can choose concurrent collection or non-concurrent collection. And again, this is the trailer version of the talk. There are basically 4 independent flavors of the garbage collector, and you can go and see what the different choices are in the matrix and see when they make sense to you, and they're configurable in a comparatively straightforward kind of way. It used to be quite difficult to accomplish that, and you'd have to be a CLR host, and who wants to do that? There are many cases where running the workstation collector, for instance, in a non-concurrent kind of mode is very appropriate even in a server context. Because the workstation collector, for instance, uses less threads, okay? And if threads are at a premium because, say, it's a terminal server, that might be an excellent choice for you. On the other hand, sometimes the raw throughput that is achieved by the server collector might be better even if you're on a workstation. And so you can make those choices as appropriate for your application, and you have to change not a line of code, right? Just a question of choosing the collector that works best for you, and you can read about those. So it's a little bit of extra flexibility for you. Okay. Some big changes in exceptions. Actually, since beta 2, there were significant changes in the performance of exceptions. So if you noticed a significant regression in performance between Everett and Whitby with the beta 2 drop, I think you'll be pleased with the release drops. And RC1 has significant improvements in this area, especially for deep stacks. So we've done a lot of work there. really, the inherent improvements in exceptions performance fall into that lovely category, my favorite one, which is you do nothing, okay? You'll just notice that the cost of exceptions is lower than it used to be, which is, my favorite kind of performance improvements. I do work, you do nothing, your application goes better, your customers are happy, you have more money in your bank account, you get to retire sooner, you get to have a better retirement location. We all want to have a better retirement location, right? Okay, so this is my way of contributing to your retirement. I'm reducing the cost of exceptions. However, we added additional features that you can opt into to avoid exceptions. In our architecture, we've optimized exceptions so that the cost of entering a try block is nothing. The cost of entering or dropping into finally blocks, nothing. These are very, very inexpensive operations. However, as a result of those choices, right, optimizing for ease and cheapness of entering blocks, when we throw, we have a greater cost because we now have to do analysis to figure out which nested blocks we're in and do a whole full unwind. And had we chosen a different path, the throw might have been faster, but at the expense of slower tries. Okay, well, we believe that we want free tries because we think tries are prevalent and normal, and we want to put the tax on the exception. But in some cases, exceptions are sort of expected, an expected exception. That's kind of a funny thing. In those cases, especially if it's an example that I gave there is try parse, there's a variety of these try methods. Okay, try parse, try this, try that. These guys give you an opportunity to get a return code for common error paths rather than a thrown exception. Because, for instance, if you're parsing a 100,000 line file and you expect that there's going to be an error every 10 lines, you don't want to raise an exception every 10 lines. The kind of guidance that I give people is that you want the exception case to be the one time in 1,000, or or maybe even less than that, right? If you're going to be significantly higher than that, you're going to find that you're paying significant tax for those raised exceptions. So take advantage of some of the methods like try parse to avoid exceptions in the common cases and handle them with standard control flow. You'll be doing yourself a big favor in terms of performance, in terms of locality and memory demand, in all the dimensions. It's much happier. Okay. Security. We did a bunch of work here too. One of the first things that I did when I joined the CLR 3 years ago was I rewrote the security parser. Well, I didn't rewrite it, but I did a bunch of optimization work in the security parser so as to reduce how much memory it needs. Now, this little guy is very important because before we can even load anybody else, right, we have to know kind of what's going on in the world, right? We have to go and look and see what permissions are active and what rights you might have and what's the current policy. And so there's some reading and parsing that we have to do. Even in the cached cases, we have to do some parsing. And so there's a little baby XML parser in our system that knows just how to parse security XML because we can't load the big XML system. You might not even have permission to load system.xml. So we have to do this, on the cheap. So that little guy is very important because he's right on the startup path. And we did a lot of work there to reduce the cost in terms of how much memory it allocates and so forth. And all of that, again, translates directly into startup savings. And it's present in Whitby. You do nothing. You just get a better parser, right? And we've done some work in terms of how asserts are evaluated so that when you go through when you go through security assert statements, right? Not debug asserts, mind you, but security asserts. So that is asserting that you have a certain permission. Those have been significantly reduced in the cost. They're practically free at this point. Additionally, the most common demands, the so-called special demands for things like where a demand for full trust is made. Many APIs require full trust in order to run. So it's common to demand full trust. It's common to demand access to unmanaged code. Every time you p-invoke, right, there's a potential that we might need to do a demand for unmanaged code access. And there's about 5 or 6 other so-called special demands. Those guys can be evaluated blazingly fast now. Only a couple of instructions are required to do a quick mask and no stack walk. So in the bulk of cases, that's really important because they happen, extremely often in partially trusted cases, doing interop and so forth. Very significant performance optimizations were realized just by changing those. Generally speaking, full trust performance now is as good as security off used to be. Okay? I mean, if I wanted to say it in a few sentences. So it used to be that, if you turn security off, you get a little bit of extra perf. You don't have to do that now. If you're running full trust, you're good to go. You're going to get those special demands are going to kick in. You're going to get very quick evaluations, and we can test for full trust in about the same amount of code as it used to take to see if security was off, which is really a great place to be. So that's good for you in terms of if you're doing rich client applications where they're running full trust locally. It's good news. If you have partial trust scenarios with extensions, the asserts and special demands are going to help you out. So across the board, you should be pleased. Reflection. We did a bunch of work in reflection associated with how we keep the data. Our old system was a little bit eager about how much memory it kept and how the reflective data structures stayed in memory over time. I mean, and I guess I'm understating it. Really, it didn't let go of anything ever. So reflection information used to sort of accumulate and accumulate and accumulate. And I have a little saying, and I'm not sure where I picked this up, but what do you call a cache with, no discarding policy? That's called a memory leak, right? Yeah, okay. So caching is all about having great policy, and the policy was somewhat lacking in this area. So significant improvements were made there, re-architecting how the stuff stays and what's durable. Additionally, there's better APIs for doing token-based access so that you can avoid re-looking up the same things. You can preserve tokens. And you can ask for exactly what you need. So in many cases, you can go and get single members and get those back and get just that data without us having to pre-populate the whole cache for the whole class, right? So, again, avoiding those eager preloading and letting you surgically get just what you need. A lot of times, we're doing reflection, but we only needed 3 fields. We needed to pick up a couple data fields so we could do a set or one invoke. And so it's very nice to just be able to go and not persist the whole class structure, not enumerate all the fields and so forth. And in many cases, we were doing operations like that internally in the past, and those are gone, right? So you should find if you're using reflection in Whitby that your overall costs of reflection are quite a bit lower. So that's really very helpful for many classes of applications. Actually, that's another good survey question. How many of you are using reflection somewhere in your application? All right. A lot of people using reflection, a lot of people. It's funny because I wonder if when the reflection stuff was first written, if people really realized how mainstream that was going to be and how important it was going to turn into with, the coming of dynamic languages and so forth. And sometimes I think that originally folks thought that was going to be much more of a fringe usage of the CLR. And as you can see by the hands you have up here, there's nothing fringe about it. That's our bread and butter. All right, profiling API. I worked on this one personally. Lots of improvements in our profiling API in Whitby, and they turn into better tools for you. We have good callbacks now for diagnostics associated with where objects are created and where they die. We have an opportunity to do asynchronous sampling for time, so you'll start to see time-based profilers that sample well and give you good results. We have one in Visual Studio Team System. Okay, all of these turn into better profiling tools for you, and if you want to see what's new and shiny in this area, all you have to look at is what's the feature set of the profiler in VSTS, and what are the new features in our new CLR profiler, right? And CLR profiler is available as a free download, so you can go and look, and you'll see we have good information about where things are being allocated and where they're dying, so you can see, hey, what's dying in generation 2? Who made that object, And those sorts of analyses are enabled. Additionally, there's features associated with object inspection. So if you're concerned about your performance, and this is a great little technique, it's very straightforward to write a simple profiler. We're going to be putting samples out on MSDN, and I believe we've already started with some of those code snippets, but you'll start to see samples of example profilers that do straightforward logging and so forth. You can extend those and have them measure things that are important to your application. Get application measurements that are critical to your business needs and correlate them with things that are happening in your system. All of those are better ways of you understanding how the system is working and where your costs are, right? And to the extent that we can tell you what the CLR costs are and how they interact with your costs, you get better information, you can make better programming decisions. That's what it's all about. So profiling API changes, write your own profilers, hook into these guys. They're very straightforward, and go ahead and get the measurements you need. We did tons more. I told you this was the trailer version of the talk, right? And I guess it is the trailer version of the talk, but I didn't even mention some of these other things. There's improvements in the thread pool. There's more adaptive stuff. We made great improvements in delegates. If any of you have used IronPython, they're reporting significant improvements in Python performance because delegates are just lots faster. So delegate dispatch, you should be pleased. There's new improvements in the string thing, in the string classes. So it's easier to do comparison by ordinal. And in fact, we did a whole paper on when you should use which kind of comparison and what the benefits are for comparing by ordinal and when that's important and what are security reasons for doing that and what are performance reasons for doing that. The string hashing functions were moved into managed code, so there's less interop and back and forth to do string hashing, so that's helpful. We got up to a 10x improvement in cross-app domain remoting for simple types. So if you're using multiple app domains, you'll be a lot more pleased with how simple things like strings and integers and value type structs and readily marshallable stuff goes. We have add memory pressure and remove memory pressure added to the GC, so you can tell us about your external memory associated with, say, bitmaps or whatever else you've got. And all of those things add up to just, an extra breadth of performance functionality. Maybe things we would have liked to have delivered in Everett and, we couldn't get to it, or things that we've noticed based on information from you guys. A good chunk of this is information that we got, from customer labs and one-on-ones and feedback on our blog. And, people are telling us, hey, we need this. Hey, we're following this pattern and the cost is too high. Give us some relief here. This reflection thing. We want more perf there. We're doing more demands. We need that. Your feedback has been very critical in getting these kinds of features into the product. And I promised the link to where you can find more information on these. I'm going to have a little posting up on my blog shortly after this, and I invite you all to ask detailed questions at that time. And I'll try to get you the particulars on any of this that resonates with you. And I keep a bibliography of other articles there, so you can. And I believe these slides are available to you on the DVD, so you can go ahead and find those. If you're looking for me, you can find me online just by searching for Rico. Go to MSN search and type Rico, and I'm like number 4. Rico Mariani's Performance Tidbits. Or maybe I'm number 5. I don't know what I am. And I wanted to leave some time for questions. I'd like this to be as interactive as possible. So if you have things you'd like to ask me about, please feel free to take a microphone. And otherwise, enjoy the rest of your day. Thank you very much for coming. And please fill out an evaluation and be gentle. Or if you're more comfortable giving questions on a one-to-one basis, I'll be here for a little while too. But I think others would like to hear your question.
Hey Rico, I had a question.
A question, yes.
During your talk, you quoted a lot of very useful sort of out-of-band statistics like memory overhead associated with certain collection classes and the effect of generics and so forth.
Yes.
Is there anywhere we could find either a cheat sheet or some kind of a list, perhaps more complete, with that kind of information, even if it's just anecdotal? Because I'm sure to be rigorous, it would be sprinkled with "it depends" and stuff like that.
Well, right. Okay. One of the reasons I didn't put a whole lot of statistics into this talk is I would have had to have 82 pages of disclaimer. Well, I measured this on this kind of processor under these conditions, blah, 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 blah. And I didn't want to bore you guys all to death. However, the particular statistics you're talking about, the cost of generics, I covered in Performance Quiz number 7, which is on my blog right now. And I went into an analysis in very great detail. Now, a colleague of mine, Jan Gray, a couple of years ago did a paper where he did a series of measurements on virtual function calls, delegate costs, memory allocation, and other basic features. I can't remember the exact title, but it was something like, CLR performance, know what things cost. I want to redo that article, and I'll probably will do that comparatively soon, with WIDBE numbers to show kind of what changed and what got better, and in some cases what got worse, right? And I'll get that out on my blog. But the best place to start that I can tell you for CLR performance information and anecdotal stuff like this is go to my blog, blogs.msdn.com/RicoM. And if you forget that, just search for Rico, okay? Just, go to pick up your favorite search engine, search for Rico Mariani Performance Tidbits. You'll find it. It's, number 5 or number 4, depending on the search engine you choose. Okay, and those statistics are covered there. Yeah.
Thank you.
I have a question in the front. Okay. Let me repeat the question for the audience. The question is, regarding object lifetime, the gentleman has experienced that objects that have been living a very long time will never, in fact, get collected and basically live forever, and is that still a problem? Well, I certainly hope not. That would be a bug. Even in the 1.0 system, it was certainly never the intent that objects that had lived beyond a certain point would stop being considered. However, it is the case that Generation 2 collects could get very, very distant, right? If the promotion rate into Generation 2 is low enough, okay, then what will tend to happen is that the collector will continue to think, Generation 2, whatever, hardly anything's happening there. It's just not worth it to look at those objects, you know? There's not enough junk in there. And so it will defer those collections. And it might defer them for a minute, 2 minutes, 5 minutes. It could be hours before the collector decided that a Generation 2 collect was worth it. And in fact, if you're in that situation, that's a good thing, you know? You do not want the promote rate to Generation 2 to be especially high. However, where you get into trouble is where a funny thing happened, an episodic thing, such as a big dialogue closed, a big document was closed. That's where you want to induce collections, because the collector's idea of what the current statistics are is wrong, right? And so it won't know that, hey, there is a bunch of death in Generation 2, even though the trends didn't predict it. And so if you're seeing objects that lived basically forever, probably that's what's happening, is they wouldn't live forever. Eventually they would be collected, but it might be quite long, right, between those Generation 2 collects because of the trending that's going on, right? Okay, so think about the episodic things that I mentioned before. And I think I am pretty much out of time, but I'm happy to take more questions in my lab. Come and visit me in 504 and sign up for a time. I'm doing one-on-one sessions. Or post comments on my blog. I'm going to open an article for general questions shortly. Okay? Thank you.